Good morning. So let's begin with the next chapter, nuclei. Okay. So now this chapter is very small, and most probably we'll complete this in today's lecture itself. Okay. So what is a nucleus? So we know from Rutherford's theory or Bohr's theory that it is the central part of an atom where the whole mass and the positive charge, entire positive charge of the atom is concentrated. Okay. So what is the nucleus? It's central part of an atom where there is the positive there is positive charge and whole mass of the atom is concentrated. In this chapter, we'll make use of a specific unit called as atomic mass unit. Okay, it's denoted by U. Now what is atomic mass unit? It is mass of a carbon 12 atom divided by 12. Okay, what is atomic mass unit? It's mass of carbon 12 atom divided by 12, right? Then now we'll define few quantities. First is the atomic number. Now what is atomic number? So nucleus consists of protons and neutrons. So Z is the number of protons in the nucleus. It is also called as atomic number. Okay, and if you have any atom, the number of protons and number of electrons in that atom would be equal. So it is also number of electrons in an atom, right? Then N is the number of neutrons in the nucleus. Okay, Z is number of protons, N is number of neutrons. So if you add up the protons and neutrons, you get the total particles inside the nucleus. They are collectively called as nucleons. Okay, so protons and neutrons, they are collectively called as nucleons. So we denote the number of nucleons by letter A, and this is also called as mass number. Okay, this is also called as mass number. So what is mass number? It is total number of protons plus neutrons, that is total number of nucleons. Okay, so it is number of nucleons inside the nucleus. Nucleons in nucleus, right? Now there are certain properties of a nucleus. So size of nucleus. So size of atom, we know it is of the order of 10 raised to minus 10 meters. Size of a nucleus is of the order of 10 raised to minus 15 meters. So what do we mean by size here? It is the radius. Okay, the size of nucleus is of the order of 1 Fermi. And what is 1 Fermi or 1 femtometer? It is 10 raised to minus 15 meters. Okay, then next is the radius of the nucleus. It's given by this formula, R is equal to R naught multiplied by A raised to 1 by 3. And what is R naught? R naught is equal to 1.2 Fermi. Okay, and A is the mass number, right? A is the mass number. So suppose you have some atom having mass number equals to A, or some nucleus having mass number equals to A, which is equal to what? Number of nucleons, right? So then its radius is given by this formula, R is equal to R naught multiplied by A raised to 1 by 3. Okay, so then next property is the density of nuclear matter is of the order of 10 raised to 17 kg per meter cube, and it is a constant. So there have been questions like this, that the density of nuclear matter, is it constant? It depends on A. Okay, it increases with A, it decreases with A, something like that. Okay, so density of the nuclear matter is what? It is constant, and it is of the order of 10 raised to 17 kg per meter cube, right? Now let's understand this formula. The radius of nucleus, R is equal to what? R naught A raised to 1 by 3. Okay, so where does it come from? So see, A is suppose the number of nucleons, right? So M is mass of nucleus, and small m is suppose average mass of one nucleon. Okay, average mass of one nucleon, that is mass of a proton or mass of a neutron. Then this mass, the total mass of nucleus, would be directly proportional to, you can say, mass of one nucleon, right? And roughly, I'm just saying roughly, we can write this mass as equal to A times mass of one nucleon. Okay, so then mass can be written as density times volume. So density times volume of a nucleus, it is equal to A times m, or at least it is proportional to A times m, right? So then you have volume equals to 4 by 3 pi r cube. Okay, volume is equal to 4 by 3 pi r cube. So then you can move that mass, density on other side. So what do you get? So you have r cube is equal to A times this mass by rho, that is some constant. Mass, average mass of a nucleon is a constant, and density is also constant. So m by rho is some constant, and therefore you can write r cube is equal to some constant times A. Okay, r cube is equal to some constant times A. And if you put A equals to 1, that is mass number is equal to 1, what do you get? You will get r equals to r naught, right? R equals to r naught, and therefore r naught cube would be equal to k. R naught cube is equal to k, and you put that back in this equation, that r cube is equal to r naught cube times A, right? And therefore now if you take cube root, what do you get? You get r is equal to r naught A raised to 1 by 3. So this is kind of understanding of this formula. Okay, r is equal to r naught A raised to 1 by 3. Is this in clear, everyone? Isotopes. Now what are isotopes? Isotopes of an element, you must have studied this in chemistry, are the atoms having the same atomic number. Atomic number is same, okay, and an element is identified from the atomic number, right? So same atomic number but different mass number, that means A is different. So what is A? So we know A is equal to n plus z, number of neutrons plus number of protons, right? So if z is same and A is different, that means number of neutrons is different. Okay, so these are the elements having same number of protons but different number of neutrons, we can say, right? So they are known as isotopes. So what are isotopes? They have same atomic number but different mass number, z is equal. Okay, for example, carbon 12, carbon 14, these are isotopes, right? So there would be 6 neutrons in this one, there are 8 neutrons in carbon 14. Okay, the next is isobars. So what are isobars? So you can identify that. So what is bar? Bar is unit of pressure, right? So it is some quantity which denotes weight. Okay, so bar is a quantity, or bar is a word which indicates weight. Okay, so atoms having same mass number, they are known as isobars. Atoms having same mass number but different atomic number, they are known as isobars. So A would be equal in isobars, right? A is equal and atomic number Z is different. So for example, you have cobalt and Fe, they have same mass number 57, okay, but atomic number is different, 27, 28, right? So these are known as isobars. Okay, and then there is another one which is known as isotones. So isotones have same number of neutrons, their atomic number is different, mass number is different, but they have same number of neutrons. So atoms with different atomic number and different mass number but same number of neutron number, they are known as isotones, right? So for an example, this is tritium, hydrogen 1 3, right? It is called as tritium. And then you have He24, helium. Okay, there are 2 neutrons here, 2 neutrons here also, right? So these are isotones. So this is clear, everyone? Then let's see an important point. This is very important. most probably there would be a question based on this one, that is mass defect and binding energy. Okay, so what is mass defect? So now see, you have n number of neutrons in an atom and there are z number of protons. So if you add up the mass of neutrons and mass of protons, right? So suppose mp is mass of one proton, so what would be total mass of z protons? It would be z times mass of one proton. Okay, so that is total mass of protons. If you add up mass of neutrons into this, so that is n times mass of one neutron, right? So our rough assumption would be this should be the total mass of nucleus. Okay, so if we don't know, there are neutrons, right? There are neutrons, protons, and there might be something else. Okay, so the total mass of nucleus should be this much or greater than this. Yes, no? Okay, for an example, you take a bowl like this and there are some marbles. Okay, 10 marbles, let's say, and suppose you measure the mass of these 10 marbles separately, then you put them in this bowl and you measure the mass of bowl with these marbles, then it should be greater or lesser. If bowl is massless, let's say, so nuclear matter is massless. Okay, so remaining nuclear matter, okay, barring the except the protons and neutrons. Suppose if there is something else, it is massless, then the mass of nucleus should be at least equal to what? Mass of neutrons plus mass of protons, right? This can be our naive guess, we can say. Okay, but on the contrary, the mass of nucleus is less. The mass of nucleus is less compared to the total mass of the protons and neutrons. So this looks like a defect, and that's why this is known as mass defect. So this is a very good word. Okay, it is known as mass defect, right? So the difference in mass of a nucleus and mass of protons and neutrons, it is known as mass defect. Okay, so what is mass defect? Now mass of nucleus is lesser compared to the total mass of nucleons. Okay, so suppose m is the mass of nucleus, m is the mass of nucleus, and this is collective mass of protons and neutrons. Okay, z into mass of proton plus n times mass of neutron. So n can be written as what? A minus z, we know that. So z into mass of protons plus a minus z into mass of neutrons, this is total mass of nucleons, minus the mass of nucleus, it is known as, minus the mass of nucleus is known as mass defect, right? So now question is, why is this mass lower? Okay, why is this mass lower? So now see, the protons, they are positively charged, electrons are not charged, right? So there is, if you take two protons together, okay, if you move them closer to each other, what will happen? They will repel each other, right? They will repel each other. Okay, so now to counter that repulsion, you need some force, that means you need some energy. Okay, and that repulsion is continuous. It's not like they will repel now and after some time they will be calm. Okay, it's not like that. They'll keep on repelling each other, so you need a continuous force. Okay, that means continuous supply of energy, right? So now inside a nucleus, the protons, they are very close to each other. So we have seen what is the radius of nucleus. It is of the order of 10 raised to minus 15 meters. Okay, it is of the order of 10 raised to minus 15 meters. We have seen that. Okay, so the two protons, you want to keep them so close, okay, inside a radius of 10 raised to minus 15 meters. Okay, so separation between them would be of the order of 10 raised to minus 15 meters. So you need a lot of energy to do that, because they repel each other, and there are, we have seen the comparison of forces. So the electrostatic force is a very strong force, right? So you need a force which is stronger than that to overcome that repulsion, and that force is known as the nuclear force. And to provide the nuclear force, you need some energy, that is known as the nuclear energy. And where does it come from? So it comes from this mass defect. Okay. It comes from mass defect, right? So there is Einstein's mass energy relation, that E is equal to mc square. Okay, this is Einstein's mass energy relation, and using that relation we can say that energy equal to this mass defect. Okay, why is effective mass of the nucleus lesser than the mass of nucleons? Because the remaining mass, you can say, it is being utilized as energy. Okay, that is equal to delta m multiplied by c square. Okay, so this is known as the binding energy of the nucleus, right? Okay, is this thing clear, everyone? Yes, no? Okay, good. So what is the binding energy? Binding energy sorry, the energy equivalent of mass defect of a nucleus is known as the binding energy, right? Binding energy will denote it by EB, and EB is equal to what? Mass defect, which is this term, multiplied by c square, using the Einstein's mass energy relation. Okay, this is using Einstein's mass energy relation. Then you can substitute delta m equals to this term. Okay, that is z into mass of protons plus a minus z multiplied by mass of neutrons minus the mass of nucleus, and it is multiplied by whole term multiplied by c square, right? Okay, and if atomic masses are expressed in the atomic mass unit, this is called as unified atomic mass unit, then that's why later u, it's denoted by u. Then binding energy is, suppose if mass defect is delta m, then binding energy would be equal to the delta m, which is expressed in what? Expressed in u. Okay, atomic mass unit. So if delta m is expressed in u, then the binding energy would be equal to delta m multiplied by 931.5 mega electron volts. Okay, so this is an important unit. Okay, we'll make use of this one, right? Okay, so then now binding energy per nucleon, next term is the binding energy per nucleon. It is the average energy required to remove a nucleon from the nucleus. So now see, what is the binding energy? If you think about for an example, if you think about an atom, so if you think of hydrogen atom, this is suppose H atom. Okay, so this is electron revolving in the first orbit, first Bohr orbit. So how much is its energy? The energy of this electron in the first Bohr orbit, we know, we studied this in last chapter itself, it's minus 13.6 electron volts. Okay, so this is the energy of electron. Now suppose you want to separate this proton and electron. What's there in the nucleus of hydrogen atom? There is only one proton. Okay, so suppose you want to separate this, so energy required to separate is known as ionization energy. Okay, or you can also call it as binding energy. Okay, what would be binding energy? Binding energy of this electron is equal to EB is equal to what? 13.6 electron volts. Okay, so it's the energy required to make this electron free. It's the energy required to make this electron free. Okay, right? That energy is known as binding energy. Okay, so see here, now inside a nucleus, so suppose this is nucleus, mass of nucleus is less than the mass of nucleons, right? So suppose there are 4 nucleons here inside a nucleus, mass of this nucleus is less than mass of nucleons. So now suppose you want to make these nucleons free, then they are separated, their their mass when they are separated from each other would be more compared to that of mass of nucleus. That means if you want to increase the mass, you will need to supply some energy, right? So that energy is known as the binding energy. Okay, so we are seeing this from different angles. So this is known as the binding energy, right? What is binding energy? The mass defect. Okay, difference in mass of nucleons and nucleus multiplied by c square. So this much amount of energy if you supply to the nucleus, then what happens? The nucleons will become free. Okay, nucleons will become free. This thing is clear, everyone? Yes, no, right? Okay, very good. Good. So then now, what is average energy required per nucleon to make it free, to remove it from the nucleus? It is known as the binding energy per nucleon. Okay, binding energy per nucleon is the average energy required to remove a nucleon from the nucleus. Okay, so EBN is what? It is average energy per nucleon. Okay, EB divided by number of nucleons. So that is delta M times 931.5, okay, mega electron volts divided by A. Now if you need lesser energy to remove a nucleon from a nucleus, that means that nucleus is weak. If you need greater energy to remove a nucleon from the nucleus, it means that that nucleus is strong, right? If you need lesser energy to remove a nucleus, that means sorry, what did I say? So if you need lesser energy to remove a nucleon from the nucleus, it means that that nucleus is weak. If you need greater energy to remove a nucleon from the nucleus, means that the nucleus is strong. Okay, so which nucleus would be stronger, whose binding energy per nucleon is greater, right? Okay, which nuclei would be on stronger side, whose binding energy per nucleon is greater, right? Is this thing clear, everyone? Okay, good. So then you have this curve called as binding energy per nucleon curve. Okay, so now this would be a discrete set of numbers, right? You will have discrete points on the map. It's not a continuous curve, right? This is an important point. Again, there can be a question like this. Why? Because see, you have hydrogen nucleus, okay, then there is deuterium, after that there is tritium, then you have helium, okay, after that you have lithium. Okay, so number of nucleons, it is not a continuous number, right? It goes from 1 to 2 to 3 to 4, okay, then there might be 5, there might be 6, right? So it changes by at least a magnitude of 1 nucleon. Okay, and then after Fe, okay, let's say for an example, suppose there is directly this atom, okay, or after sulfur, suppose there is directly Fe, okay, so there is nothing in between, right? So it's not a continuous graph, it is discrete points. Okay, these are discrete points, please remember that. Okay, so what we are plotting here is binding energy per nucleon versus the mass number. Okay, binding energy per nucleon versus the mass number, and you can easily see if mass number is small, then binding energy is very low. So this is in mega electron volts. Okay, the unit for this one is mega electron volts. So for deuterium it's under 2 mega electron volts, for tritium it's under 4 mega electron volts, then you have lithium under 6 mega electron volts, okay, helium slightly stronger, it is close to 7 mega electron volts. Then you don't need to remember these values, right? So there is certain analysis of this curve that we need to remember. Okay. Then for carbon, it has increased from there. Okay, from helium to lithium it goes down, then it increases for carbon 12, then again it decreases for what is this thing, nitrogen, right? Yeah, nitrogen. Okay, so on and so forth, you have different values. So highest value of this binding energy per nucleon is for Fe56. So which would be the strongest nucleus? It's Fe56, right? Then this binding energy per nucleon decreases on this side also and on this side also. Okay, so binding energy per nucleon decreases on this side, means if mass number is less, and if you increase the mass number, then again the binding energy per nucleon decreases. Okay, so these are certain points to be remembered for binding energy per nucleon versus A curve versus mass number curve. So binding energy per nucleon is nearly constant, that is independent of A, for mass number between 30 and 170. Okay, if mass number is between 30 and 170, then binding energy per nucleon is fairly constant. So what does it mean? The most stable nuclei, they lie in between the mass number 30 and 170. Okay, so if mass number is between 30 and 170, you can say the nucleus is stable. Okay, then the binding energy per nucleon is lower both for A less than 30 and A greater than 170. Okay, binding energy per nucleon is lower both for A less than 30 and A greater than 170. Okay, then binding energy per nucleon has maximum value 8.75 mega electron volts for A equals to 56. Okay, and the minimum value 7.6 mega electron volt for A equals to 238. So that is after 30. Okay, minimum value right, because for deuterium, tritium, etc., the value is very low. We have seen that. So minimum value of 7.6 mega electron volts for A equals to 238. Okay, so you need to remember these points. So now see, if mass number is between 30 and 170, the nuclei are stable. Okay, that means if mass number is less than 30 and greater than 170, then what happens? The nuclei, that nucleus is not stable, right? For a certain nucleus, if mass number is less than 30, it's not stable. If it is greater than 170, it is also not stable. So most of the nuclear reactions depend on this thing, the stability of nucleus, right? Not most of the, all of the nuclear reactions depend on the stability of nucleus. So the nuclei having small mass number will have tendency to fuse together. Okay, so we are going to see that reaction. It is known as nuclear fission, sorry, nuclear fusion. Okay, fusion means they want to see, it's like human tendency. Okay, so somebody who is very slim wants to gain weight. Okay, and somebody who is very fat wants to lose weight. Okay, everybody wants to be at equilibrium. What is equilibrium? So not so slim, not so fat, right? Okay, so this nuclei also, they try to do that. That means nuclei having very small mass number, they fuse together so that the mass number would increase. Okay, so that is nuclear fission, sorry, nuclear fusion reaction. Okay, and the nuclei having greater mass, they tend to break, okay, into two or more nuclei, right? So that is known as nuclear fission. And they can lose mass in several ways. So one is nuclear fission. That means a heavy nucleus breaks into two or more nuclei. Or there is one more thing called as radioactivity. Now radioactivity is deleted from our syllabus. But what is radioactivity? So these nuclei, these nuclei, they emit alpha, beta or gamma radiations. Okay, in short. So what is alpha? Alpha is helium nucleus. What is beta? Beta is electron or a, a particle having positive charge, okay, as that of electron, but same mass, which is known as positron. Okay, so there is beta minus, beta plus. Okay, and gamma, gamma means light. Gamma means what? Light. Okay, so in nutshell, all nuclear reactions can be explained in this way. So all nuclei, they tend to achieve stability. They want to achieve stability, and that's why these nuclear reactions happen. Okay, they want to increase their binding energy per nucleon, EBN. This thing is clear? Okay, good. Then now let's talk about a force which binds these nucleons together. It is the nuclear force. So nuclear force holds the nucleons together, right? Nuclear force holds the nucleons together, and nuclear force is independent of charge. So there are protons and neutrons inside the nucleus. So this nuclear force is not biased at all. The force between two protons would be same as that of force between a neutron and a proton, and it's same as that of force between two neutrons. Okay, so nuclear force is independent of charge, does not depend on the charge, right? Nuclear force does not depend on the charge. So then nuclear force is much stronger compared to that of the electromagnetic force. In fact, it is the strongest force in the universe, and the gravitational force. The nuclear force is much stronger compared to electromagnetic force and the gravitational force. And there is one more called as weak nuclear force. So the nuclear force that we are talking about is a strong nuclear force which binds the nucleus together. Okay, and the range of this nuclear force, it is of the order of 1 femtometer. The range of nuclear force is of the order of 1 femtometer. Okay, so you can imagine if the range of this force would have been a little bit more, let's say if nuclear force acted up to the size of an atom, then all matter would have fused together, right? So range of nuclear force is what? It is of the order of 1 femtometer. Okay, good. So then let's see next point, nuclear fission and nuclear fusion. Okay, the reactions. The breaking of a heavy nucleus into two or more fragment nuclei with release of a huge energy is known as nuclear fission. Okay, the breaking of a heavy nucleus into two or more fragment nuclei with release of huge energy is called as nuclear fission. So for an example, you have uranium 92 235. Okay, so its atomic number is 92, mass number is 235, and this nucleus plus a neutron gives rise to barium and krypton, right? Its atomic number is 56, mass number is 144, 141. Atomic number of this one is 36, 92. Mass number is 92, right? Plus you have three neutrons. And it also energy of 200 mega electron volts is emitted, right? Also the energy of 200 mega electron volts is emitted. So this nucleus, heavy nucleus, is breaking into these two small nuclei. Okay, so this is known as a parent nucleus, and these are known as daughter nuclei. Okay, simply because this is breaking into these two. Okay, so this is nuclear fission, very simple, right? And then there is another reaction called as nuclear fusion. So when two or more light nuclei are combined to form a single nucleus with release of huge amount of energy, it is known as nuclear fusion. And for an example of nuclear fusion, you have two hydrogen, actually this is two deuterium nuclei, okay, they combine to form helium and release this much amount of energy, 24 mega electron volts, right? So energy is released both in nuclear fission as well as nuclear fusion. Okay, energy is released both in nuclear fission as well as nuclear fusion. And what can you say about the binding energy per nucleon of the reactants and product? So if this is reactant, okay, or you can say this is parent nucleus and these are daughter nuclei, then what can you say about EBN of them? Which one would be greater? Yeah, the binding energy per nucleon of daughter nuclei would be greater. Okay, in this case, two deuterium they fuse to form one helium. So this is fusion. So in case of fusion also, compared to that of reactants, let's call them reactants and products. Compared to that of reactants, the binding energy per nucleon of product would be greater. Okay, so let's just note this down. And this should be obvious actually, because this whole game happens because of what? Nuclei want to achieve stability. Okay, their binding energy per nucleon is less, right? So they want to achieve stability, means binding energy per nucleon should be greater. Okay, and for that sake the nuclear fission happens, nuclear fusion also happens, okay. So what we can say is the EBN of products of the nuclear reaction is greater than the EBN of reactants, that is always, okay. And energy is released both in nuclear fusion and nuclear fission. Okay, nuclear fission, in nuclear fusion as well as nuclear fission. Okay, now we make use of this reaction, the nuclear fission, to produce electricity. Okay, so there are nuclear power plants where we make use of nuclear fission to convert this energy to what? The electrical energy. Okay, we make use of this one, and the stars shine because of nuclear fusion. Okay, so we get the energy from sun. So what kind of reaction, nuclear reaction, takes place on sun, on the surface of sun? It is the nuclear fusion. Okay, so now nuclear fusion will happen at very high temperatures. Nuclear fusion happens at very high temperature, okay, which is very difficult to achieve on earth, right? So why is it so? Because to fuse nuclei, what do you need to do? You need to bring them close to each other. Okay, you need to bring them close to each other, right? So the kinetic energy that you provide It depends on what? We have studied the kinetic theory of gases. Depends on the temperature. Okay, kinetic energy is equal to what? It's 3 by 2 kBT. So suppose you want to fuse two protons together, or a proton and neutron together, then the kinetic energies must be very high, right? So that they will overcome two protons, let's say two protons together you want to fuse, then the kinetic energies must be very high so that they will overcome the electrostatic repulsion, right? Nuclear fusion happens at very high temperature, okay, of the order of thousands, right? Thousands of kelvins. Okay, actually uh, this is several thousands of kelvins. Okay, let's say 10,000, something like that. Okay, because, and reason for this is, since the ke of the nuclei that are the parent nuclei, you can say, okay, must be greater, should be greater than the electrostatic repulsion. Okay, so these are few points to be remembered in case of nuclear fusion and nuclear fission. And there is one more thing. So we have seen that nuclear fusion and nuclear fission both are exothermic. Now why it would be so? So see the reason. Now suppose this is 0 and okay, so this is the binding energy. This is binding energy of reactants, let's say. This is EBN. Okay, so this is energy of nucleus, and this is energy of free nucleons, right? Energy of a nucleus means total mass of the nucleus, you can say, convert it to C square. It's less compared to what? Energy of free nucleons. So this is EBN. Okay, so this is for reactants, let's say. So then what happens in case of products? So in case of products, the separation of energy between the free electrons and the nucleus is very high, right? Separation of the energy, that means energy required to free the nucleons, is very high. So suppose this is binding energy of products. Okay, so this is for reactants, one is for reactants and one is for product. Okay, so this is again the energy of nucleus, this is energy of nucleus of reactants. So now energy of free nucleons would be at the same level because the number of nucleons will not change in reactants and products. So energy of free nucleons is at same level because same number of nucleons are there in the reactants as well as product. Okay, but if you think about the binding energy of reactants is less compared to that of binding energy of products. So the energy of the nucleus, the reactant nucleus or parent nucleus, you can say, must be greater compared to that of energy of the daughter nuclei or the product, right? Okay, energy of nucleus, but which nucleus? Product. Okay, so there is some separation, there is this much difference between their energies. And where does this energy go? Where does this energy go? So this much amount of energy difference, this much amount of energy would be emitted, right? So energy equal to delta E, therefore energy equal to delta E, delta E is emitted in nuclear reaction. Okay, is this thing clear, everyone? And this is known as Q value of the reaction. It's known as Q value. All right. So is this thing clear to everyone? Yes, no, tell me. Why is energy always liberated? Why it is always exothermic reaction? Why not endothermic reaction? This is the reason for that. Is it clear? Not clear? Tell me. Everyone? Okay, good. All right. So then let's see some problems based upon this. Okay, and this is the theory of nucleus. Okay, it's complete. Sorry, nuclei. All right. So this is the theory of your chapter nuclei. Now let's see some problems based upon this. A nucleus represented by the symbol X, A, Z. Okay, has, what does it have? Z neutrons and A minus Z protons. This is very, very simple, right? Tell me. So option B, Z protons and A minus Z neutrons, right? Very simple. Okay, let's see next one. The mass number of nucleus is always less than its atomic number, always more than its atomic number, sometimes equal to atomic number, sometimes less than, and sometimes more than its atomic number. Tell me. Mass number of a nucleus is, it's option C, sometimes equal to the atomic number. In what case is it equal? Hydrogen 1 1, right? Atomic number and mass number is same. Okay, apart from that, if you think of any nucleus, okay, any other nucleus, the mass number would be greater, right? He 2 4. So A is equal to 4, Z is equal to 2. Okay, but there is this exception, and that's why sometimes it is equal to atomic number, right? It's not sometimes, it is only once. All right, or it can happen when you remove all of the neutrons. If you take some atom, let's say He, you remove all of the neutrons from it, then atomic number and mass number will become equal. Okay, so sometimes it is equal, but otherwise A is greater. So A is greater than or equal to Z, right? This is very simple. Let's see next one. The nuclear radius of aluminium is 3.6 Fermi. Okay, Al 27 is 3.6 Fermi. The approximate nuclear radius of copper. Okay, 64 in Fermi is. Tell me. So we know this formula, R is equal to R naught A raised to 1 by 3. This is very simple. So what we can say is R2 by R1 is equal to R naught A2 raised to 1 by 3. Okay, and R1 is R naught A1 raised to 1 by 3. So suppose 1 is aluminium, right? 1 is aluminium and 2 is copper. So we want to find out R2. Okay, so R naught will get cancelled, and you have A2 by A1 raised to 1 by 3 is the ratio of their radii, right? So this is 64 divided by 27 raised to 1 by 3. So tell me, what's 64 is cube of 4, no? Yes, 4, and 27 is cube of 3. Option 4. Okay, let's see. So this is 4 by 3, right? This is equal to 4 by 3, and therefore R2 is equal to 4 by 3 times R1, and that is 4 by 3 multiplied by 3.6. 3.6 divided by 3 will give you 1.2. 1.2 multiplied by 4 gives you 4.8. Okay, so 4.8 would be the answer. Option C. Okay, did you say option C, Nikita? Okay, good. All right, so this is very simple, right? Most of the problems would be simple like this. Two nuclei have their mass numbers in the ratio of 1:3. Ratio of their nuclear densities would be, tell me. Option B, very good. It's 1:1. So nuclear density is constant. Okay, we have seen this nuclear density is constant. Good. That is very simple. Okay, let's see next one. The radius of germanium nuclide is measured to be twice. Okay, this should be nucleus, I guess. Anyways, so nucleus, germanium nucleus radius is twice that of, what is this, Be49, barium, beryllium. The number of nucleons in germanium are, tell me. The radius of germanium nucleus is measured to be twice the radius of beryllium. The number of nucleons in germanium are, so this is very simple. Okay, so R2 is equal to twice of R1. This is given. Okay, so that is R2 can be written as what? It is A2 R naught raised to 1 by 3. Oh, what did I do? R naught multiplied by A2 raised to 1 by 3, and this should be equal to 2 times of R naught multiplied by A1 raised to 1 by 3, right? Because R is equal to R naught A raised to 1 by 3. Okay, so R naught will get cancelled, and you have A2 raised to 1 by 3 is equal to 2 times of A1 raised to 1 by 3. So then just take cube of both sides. So then what do you get? A2 is equal to 8 times of A1. That's it. Very simple, right? 2 cube is 8, and that is 8 times of, what is A1? A1 is equal to number of nucleons in beryllium, so that is 9. So 8 times of 9, that's 72, right? So answer is 72, option A. Okay, very simple. Yes, no? Clear, not clear? Okay, good. Let's see next one. The volume occupied by an atom is greater than the volume of nucleus by a factor of about. Tell me. Option B. Option D. Yeah, option D is correct, right? Because radius of the atom is of the order of 10 raised to minus 10 meters. Radius of nucleus is of the order of 10 raised to minus 15 meters. So what is the order of magnitude difference between the radius of atom and nucleus? So radius of atom, you can say radius of atom is 10 raised to 5 times of radius of nucleus. Okay, it is of the order of 10 raised to 5 times radius of nucleus, and therefore if you take volume of atom would be cube of this, so that is 10 raised to 15 times the volume of nucleus, right? So this is very simple. So option D is the answer. Very simple. Let's see next one. A nucleus ruptures into two nuclear parts which have their velocity ratio equal to 2:1. Okay, so you have a nucleus, it breaks into two parts. One goes, let's say, this way, the other one will go this way, and suppose velocity of first one is v1, velocity of second one is v2. What's given? The velocity ratio is equal to 2:1. Okay, so v1 is equal to 2 times of v2 in magnitude, right? Magnitude is 2 times of v2, but velocities are in different directions. What will be the ratio of their nuclear size? Okay, this is the question. What is the ratio of their nuclear size? So this is very simple. What we'll do is we'll make use of law of conservation of momentum. Okay, law of conservation of momentum. Okay, so momentum before it breaks was equal to 0. Momentum after breaking should also be equal to 0. So therefore m1 v1 plus m2 v2 must be equal to 0. So that is 0. So then what do you have? Therefore you have m1 v1 is equal to minus of m2 v2. m1 v1 is equal to minus of m2 v2, and if you take its magnitude, we want just magnitude. Okay, so m1 v1 would be equal to m2 v2, right? We are just taking magnitude of that. So then you have v1 equals to 2 times of v2, just put that. So then you have v1 equals to 2 times of v2. So v2 and v2 gets cancelled out. So m2 is equal to, you get 2 times of m1. From that m2 is equal to 2 times of m1. And what does it mean? You want to find out ratio of their nuclear size, nuclear radius. So mass would be proportional to, mass of the nucleus would be proportional to the number of nucleons. More is the number of nucleons, more would be the mass, right? And therefore you can say A2 is equal to 2 times of A1, right? So R2, if you want the ratio of R2 to R1, it would be equal to what? It is R0 A2 raised to 1 by 3 divided by R0 A1 raised to 1 by 3, and R0 gets cancelled, right? Or we can directly write down it's A2 by A1 raised to 1 by 3. Okay, it is A2 by A1 raised to 1 by 3. Okay, so this is very simple. Let's make some space. So that is equal to what? This got cancelled. A2 by A1 raised to 1 by 3 means 2 by 1 raised to 1 by 3. Okay, 2 raised to 1 by 3 is to 1. But this is R2 is to R1. What do you want? You want R1 is to R2, no? Okay, you want R1 is to R2. What will be ratio of their nuclear size? It will be 1 is to what? 2 raised to 1 by 3. Okay, that would be the answer, right? It's option D. Okay, this is clear, everyone? Okay, all right, good. Let's see. Let's see next one. If the nucleus of aluminium Al has nuclear size of about 3.6 femtometers, okay, then this is Te. What is Te? Te 32, 135, 125 would have its radius approximately as, yes, what is tellurium? Okay, good. All right, so then we want to find out its radius. So again, this is similar. Okay, so let's use the same formula. R2 by R1 is equal to what? A2 by A1. Now we don't need to write down R0 because we have practiced it enough. Okay, so we can directly write down R2 by R1 is equal to A2 by A1 raised to 1 by 3. And that is 125 divided by 27 raised to 1 by 3. Okay, so 125 is cube of 5, right? 27 is cube of 3. So this is 5 raised to 3 raised to 1 by 3. Okay, so that means it gives you 5, and this thing gives you what? 3. So the ratio is 5 is to 3, and therefore R2 is equal to 5/3 of R1. So 5 by 3 times of 3.6, and that is 1.2 times of 5 means 6, right? 6 femtometers is the answer, option D. Okay, so very simple, similar question. Let's see next one. The energy required to break one bond in DNA is 10 raised to minus 20 joule. This value in EV is nearly. Okay, so this is nothing, right? Very simple question. So energy in joule is given. So E is equal to 10 raised to minus 20 joules. So what would be energy in electron volts? Okay, we know that 1 joule is how many electron volts? 1.6 multiplied by 10 raised to minus 19, right? Sorry, 1 electron volt. 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. So what would be 1 joule? Just take this thing on other side. So you have 10 raised to minus 20 divided by 1.6 into 10 raised to minus 19. So this is 10 raised to minus 1. So 0.1, or you can say 10, right? 10 into 10 raised to minus 2 divided by 1.6. Okay, this is 0.1. So I can write it as 10 into 10 raised to minus 2. Okay, so this thing will give me what? 16, 6 or 96. There is 6 in all of the options. So 6 into 10 raised to minus 2. Okay, or 0.06. There is nothing in this question, right? Very simple. Okay, but they will not ask this kind of question every time. It was asked in NEET 2020. Okay, that means by NTA only. Anyways, this is clear. Okay, good. Let's see next one. The energy equivalent of 0.5 gram of substance is. So tell me, what should you do here? Oh, this is also from NEET 2020. Yeah, tell me. What will you do here? It's very simple. Mass is given. You want to find out energy. You have Einstein's mass energy relation, right? E equals to mc square. Okay, so that is 0.5, mass is 0.5 in grams. 0.5 multiplied by 10 raised to minus 3 multiplied by c square. So what is c? C is 3 multiplied by 10 raised to 8, and you have square of that. That's it. 3 square is 9. Okay, so 0.5 times 9 multiplied by, you have 10 raised to minus 3 multiplied by 10 raised to 8 times 2 is 16. 16 minus 3 is 13. Okay, and this is 4.5 multiplied by 10 raised to 13, right? 4.5 multiplied by 10 raised to 13 joules. Okay, so this is very simple. So option B. Okay, this is clear. All right, good. So then let's see next one. How does the binding energy per nucleon vary with the increase in the number of nucleons, or you can say increase in mass number? Decrease continuously with mass number. First decreases, then increases with increase in mass number. First increases and then decreases with increase in mass number, and increases continuously with mass number. Tell me. Binding energy per nucleon. It's very simple, no? We had seen this curve, binding energy per nucleon curve. It starts like this, then it goes like this. So EBN versus A curve, first binding energy increases, then it goes on decreasing. Okay, so first increases and then decreases with increase in the mass number. It's option C, right? Okay, this is very simple. All right, let's see next one. The mass of lithium 37 nucleus is 0.042 U, less than sum of the masses of all its nucleons. Okay, the binding energy per nucleon of lithium nucleus is nearly. Tell me, what should we do? What's given? Delta M is given, and it's equal to 0.042 U. Okay, so if we know delta M, then we can very easily find out the binding energy. What would be binding energy? EB is equal to 0. That is delta M multiplied by 931.5 mega electron volts, right? 931.5 mega electron volts. That's simple. And you want binding energy per nucleon. So EBN, binding energy per nucleon, is just equal to EB divided by number of nucleons. So that is delta M times 931.5, this would be in mega electron volts, divided by number of nucleons. Okay, A. So what is delta M? 0.042. 0.042 times you have 931.5 mega electron volt, and all of the options are given in mega electron volts, no? So let's keep it in mega electron volts only. 931.5 and divided by A. What is A? A is 7, right? So it is lithium 37, mass number would be 7. Then you have 7, 6 are 42, right? 7, 6 are 42. This would be 0.006, or you can say it is 6 multiplied by 10 raised to minus 3. Okay, if you divide this thing by this thing, then you need to multiply that by 931.5. This will be little bit lesser than 6. Okay, so if it was 1000, then that 1000 and 10 raised to minus 3 would have got cancelled out, but this is slightly less than 1000. Okay, 931.5. That means the answer won't be 6 mega electron volts, it would be lesser than that. Okay, so 5.6 mega electron volts, right? That would be the answer. This is clear, everyone? All right, good. Let's see next one. If M, Az, Mp and Mn denote the masses of nucleus, okay, X, Z, A, proton, neutron respectively. So this is mass of nucleus, this is mass of proton, this is mass of neutron in units of U, and binding energy B represents its binding energy in mega electron volt, then tell me which one is correct. So you know that binding energy is equal to delta M times C square, right? Okay, so you can move that C square on other side. You can move C square on other side, then you get binding energy because there is no C square in this one and in this one. Okay, so binding energy by C square is equal to delta M, and that is equal to what, Z times mass of proton plus A minus Z times mass of neutron. Okay, they are denoting it by capital M. Okay, minus the mass of nucleus, and mass of nucleus they are representing like this. So MAZ, right? Then okay, so move this thing on this side and this thing on the other side. So what do you get? Therefore you get mass Az is equal to, okay, so mass Az on left hand side, it becomes positive. Move this thing on other side. Okay, so what do you get? You get Z times mass of proton plus A minus Z times mass of neutron minus binding energy divided by C square. So it is option C. Okay, it's option C, right? Yes, no? Okay, so this is simple. All right, let's see next one. A nucleus, this nucleus has mass represented by this thing. Is it the repeated? No, it seems different. Okay, a nucleus has mass represented by this thing if Mp and Mn denote the mass of proton and neutron respectively. Binding energy in mega electron volt. V is binding energy in mega electron volt. Which one is correct? It should be Z into mass of proton plus A minus Z into mass of neutron minus the mass of, yeah, that option A itself is correct. Okay, so these are, at least this one is direct question, right? Okay, binding energy is delta M into C square. This is a direct question. Okay, good. Let's see next one. Fission of nuclei is possible because the binding energy per nucleon in them increases with mass number at low mass numbers, decreases with mass number at low mass numbers, increases with the mass number at high mass numbers, decreases with mass number at high mass numbers. Tell me which one is correct. Where will the fission happen? A light nucleus or in heavy nucleus? Light nuclei or heavy nuclei? Heavy, no? Good. Okay, so what happens then for heavy nuclei? The binding energy per nucleon increases or decreases? Decreases. Okay, so answer is decreases with mass number at high mass numbers. Okay, so fission will happen for the nuclei which have high mass numbers, right? And binding energy decreases. So this is simple, right? Yes, no? Okay, Nikita, Selvakumar. All right, good. Let's see next one. The mass of proton is this much and that of neutron is this much. The binding energy of He is. So again, same kind of question. Okay, so questions are repeated in this one. Repeated meaning the questions are of same type. Okay, tell me what would be its binding energy given that helium nucleus mass is this much. So you just need to find out the mass defect. Okay, so find out mass defect. So that is equal to how many protons and neutrons are there in helium. So okay, let me just write down the formula. Z times mass of proton plus A minus Z times mass of neutron. Okay, and minus the mass of nucleus minus M. So it is 2 times mass of proton, right? Number of protons and neutrons in helium is just 2. Mass of proton is 1.0073 U. Okay, everything is in U. Let's just remember that and calculate. So 2 times mass of a neutron is 1.0087 and minus we have mass of this nucleus, helium nucleus is 4.0015. What is this? Okay, what's the answer of this one? So you have 73 times 2, that would be 146, right? So 2.246, sorry, 2.0146 plus then 87 times 2 should be 176. Okay, plus 2.0176. No, this should be 174. No, sorry, 174. Okay, minus you have 4.0015. Just add this up. 6 plus 4 is 10. Okay, then 7 plus 4 is 11. 11 plus 1 is 12. Okay, 1 plus 1 2 plus 1 3. 320. So it is 4.0320 minus you have 4.0015 and that's equal to what? 0.00305 U. Okay, some calculation and then tell me if it's correct. Right, what would be binding energy? So EB is just equal to delta M in atomic mass unit multiplied by 931.5 mega electron volts. So 0.0305, it's 305 multiplied by 10 raised to minus 4. Okay, times you have 931.5. So 931.5. All right, so this is 305 times 931.5 should be lesser than or let's write this thing as 305 times, okay, if it was 1000, then you will have 305, okay, 305 into 10 raised to 3 multiplied by 10 raised to minus 4, so that's 10 raised to minus 1. So 305 times 10 raised to minus 1 means 30 point something, 30.5, should be slightly less than that mega electron volts. Oh, other options are very far, okay, so it is 28.4 mega electron volts. That should be the answer. Okay, tell me, is it correct? Yes, no? Okay, check the calculation. This was correct, right? Okay, good. Let's see next one. In any fission process, the ratio mass of fission products divided by mass of parent nucleus is, tell me. Mass of products divided by mass of nucleus, parent nucleus. So it's less than 1, right? It's less than 1. How? So simply you can put it this way: if binding energy is more, mass would be less. Okay, binding energy is more means mass is less, right? What's binding energy? So binding energy is proportional to mass defect, right? And what is mass defect? Compared to free nucleons, how less is the mass of nucleus? That is mass defect. Okay, how much less is the mass of nucleus compared to free nucleons is the mass defect. So binding energy would be more if mass defect is more. Mass defect would be more if mass of nucleus is less, right? And we know in case of fission or fusion, in both cases, what happens? The binding energy of the products is greater than EBN of products is greater than EBN of the reactants, right? And therefore, if EBN is greater, then that means that delta M of products, okay, products is greater than delta M of reactants. Delta M is greater. Now number of nucleons would be conserved in nuclear reaction. Okay, so compared to that of free electrons, mass of, okay, delta M is greater means the mass of nucleus would be smaller, right? Therefore the defect is greater. Okay, you got it? Mass of the nucleus would, if it is smaller, then the defect, mass defect would be greater. Okay, this thing is clear. So therefore, or let me write it this way. So mass of, what is mass defect? Mass of, even if you know, that's very good. If you are understanding it, it's very good. Otherwise what we can do is mass of free nucleons, okay, M of free nucleons, let's say, minus the mass of product nucleus. This thing is greater compared to mass of free nucleons, right? What is delta M? It's mass of free nucleons minus mass of these are reactants nucleus, okay, reactant nucleus. Okay, so then you can cancel out this thing. So minus the mass of products nucleus is greater than minus the mass of reactant nucleus. But if you remove the negative sign, what will happen? This proportionality will flip. Okay, so therefore mass of product is less than mass of reactant. Is this thing clear, everyone? And if it is so, then if you take ratio of mass of product to mass of reactant nucleus, then that would be less than 1. You move this thing on other side. Okay, everyone, is it clear? So you can remember it this way: binding energy is more, mass would be lesser. Okay, binding energy is more means mass would be lesser, right? Let's see next one. In nuclear fusion process, the masses of fusing nuclei be M1 and M2, and the mass of resultant nucleus be M3. Okay, so again, what is the answer of this? So mass of product is less than the mass of reactants, because binding energy of product is more than the binding energy of reactants. Mass of product M3 is less than M1 plus M2. Okay, be it nuclear fusion or fission, it's always true. It's option C. Okay, this is clear. Right, everyone? Okay, good. Let's see next one. Solar energy is mainly caused due to burning of hydrogen in oxygen, okay, fission of uranium present in the sun, fusion of protons during the synthesis of heavier elements, and gravitational contraction. What's the reason? Solar energy is produced because of what? Fusion of protons, okay, during the synthesis of heavier elements. So protons combine to produce heavier elements, right? That's the reason of solar energy. Let's see next one. Okay, so this is again NEET 2020 question. When uranium isotope U-92-235 is bombarded with a neutron. Okay, so neutron has no atomic number. For a neutron, atomic number is 0, mass number is 1. For a proton, okay, remember this, for a proton, atomic number is 1, mass number is also 1. For electron, atomic number is atomic number is -1, mass number is 0, right? For neutron, atomic number is 0 because there is no charge, you can say. Okay, mass number is 1 because it has mass of nearly 1 U. Okay, proton has mass of 1 U nearly, and it has positive charge, so its atomic number is equal to 1. Electron has same amount of negative charge, so its atomic number is -1, but mass is negligible. Okay, it's 2000 times less than that of mass of proton, so mass number is 0. Okay, and in case of positron, now I guess it will not come, it's 1 0. Okay, so this is positron, so this is E minus, this is E plus, right? Okay, so this thing is clear, everyone? Atomic number and mass number of these particles. Okay, good. So then you have uranium plus this neutron, one neutron, and it gives rise to the fission reaction. Krypton 3689 plus suppose some X, whose atomic number, mass number we don't know. Okay, plus you have 3 neutrons. Okay, 3 neutrons. So 3 times of a neutron, that is atomic number is 0, mass number is 1. Okay, so just calculate, we want to calculate Z and A. So the atomic number and mass number should be conserved in a reaction. Okay, the total atomic number and total mass number should be conserved. So atomic number of reactants is equal to atomic number of sum of atomic number of reactants is sum of atomic number of products. Okay, so Z is conserved and A is also conserved. So from conservation of atomic number, what do we get? 92 plus 0, right? 92 plus 0 is equal to 36. Okay, plus Z, which we don't know. Okay, plus 0. Atomic number here is 0. Okay, so therefore Z is equal to what? It's 92 minus 36, and that's equal to 92 minus 40 will give me what? 52. 52 plus 4, 56. Okay, so 56. So it is option A only. That's the answer, right? So here itself you get the answer, but if you want to confirm, then you can check it using the conservation of mass number. Okay, A is also conserved, right? So what is A here? What is mass number? 235. 235 plus, this is only one neutron, so 1 plus 1 should be equal to 89 plus A plus, this is 3 times 1. Okay, so that's 3. So therefore this is 236 minus, this is 89 plus 3 is 92, right? So A must be equal to 236 minus 92, and how much is it? So if I subtract 100 from here, it would be 136, but then I have subtracted 8 extra, so add up 8. Okay, so it would be 144, right? 144. So it's option A. Okay, this is clear. Everyone? Okay, good. All right. So see, you might have seen my weird way of calculation. This will help, right? So if you do 236 minus 92, it takes time. Okay. So what I did is 236 minus 100, 136. But I have subtracted 8 extra. So I will add 8, right? So this is this might seem weird, but it will save time. Anyways, let's see next question. A certain mass of hydrogen is changed to helium by the process of fusion. The mass defect in fusion reaction is this much. The energy liberated per U is, okay. So mass defect is given, no? There is nothing. Okay, mass defect in the fusion reaction is the difference in masses of the reactants and product nuclei. Okay, so delta M is given, so it is 0.02866. Therefore what would be the energy liberated? Energy liberated would be equal to delta M multiplied by C square, but this is given in U, so just multiply it with 931 mega electron volts. It is 931.5, but here they have given 931. Then question is, energy liberated per U is, what is energy liberated per U? Okay, so how many nucleons are there? How many nucleons are there? Certain mass of hydrogen changes to helium. Hydrogen 1 okay, plus hydrogen 1 but you want helium, no? So there are 4 nucleons. Okay, so it should be by some way. What happens, the hydrogen becomes deuterium and then it fuses, right? So there are 4 nucleons, so therefore you want energy liberated per nucleon. So that is E per A would be equal to what? Delta M times 931 divided by 4. Okay, just put the values. What is delta M? Delta M is 0.02866 times you have 931. Okay, so this thing divided by 4 will give me what? Okay, see, in this kind of question, keep 931 as it is always, because this is close to slightly less than 1000, but it is good for rough approximation, right? So let's keep it like this, so it's nearly 1000. Okay, so then divide this thing. So you have E by A, energy liberated per nucleon, is 0.028. If you divide this thing by 4, it will give you 0.00007, right? 0.007 and something extra. Okay, 0.007 times 931, right? So if it was 1000, then the answer would be 7 mega electron volts, but this is not 1000, it's slightly less than that, so 6 point something. Okay, so 6.675 mega electron volts, right? This is clear, everyone? Okay, there is nothing in this question, right? Okay, good. Let's see next one. Fusion reaction takes place at high temperature because we had seen the reason for this at the beginning only. The nuclei break up at high temperature. Atoms get ionized at high temperature. Okay, that is also true. Atoms get ionized, but that's not the reason for fusion reaction. Kinetic energy is high enough to overcome the Coulomb repulsion between nuclei. This is the reason. Okay, kinetic energy is high enough to break the Coulomb repulsion between the nuclei. This is the reason, right? So molecules break up at high temperature. Okay, so this is the reason, right? Kinetic energy is high enough to overcome the Coulomb repulsion. So this is simple. Let's see next one. Binding energy per nucleon in deuterium and helium nuclei are this much and this much respectively. When two deuterium nuclei fuse to form a helium nucleus, the energy released in the fusion is, what is energy released in the fusion? This is the question. So two deuterium H12 they fuse to give helium, okay, plus some energy Q, or let's call it E or Q, doesn't matter. Okay, so how much would be the energy? So binding energy of reactants is what? B of reactants. Okay, so let's call it, let's name it something. So BER is equal to binding energy of reactants, right? And suppose BEP is the binding energy of products. Okay, binding energy of product. Here we have only one product, right? So then binding energy of reactants is how much? That's equal to 2 times of 1.1 mega electron volt, because you have two reactants. Binding energy of product, you have only one nucleus of helium, 7 mega electron volts. So how much of energy is liberated? You have simple formula. It's binding energy of product minus the binding energy of reactants. Okay, yeah, that's it. Binding energy of products minus binding energy of reactants, right? If it was mass defect, then you will have mass defect of product, delta M of product, minus mass defect of reactants into C square. Okay, so this is 7 minus, you have 2 times 1.1, 7 minus 2.2, how much is it? 4.8, right? But there are 4 reactants and products, I mean 4 nucleons. This is binding energy per nucleon, no? So how many are there? Okay, so binding energy of product, binding energy per nucleon is 7. How much would be the total binding energy? There are 4 nucleons, right? 4 nucleons. So it is 4 times of 7. Okay, and binding energy per nucleon of reactants. So here also there are 4 nucleons. So it is 4 times of 1.1. Okay, so this is 28. And how much is this? 4.4. 28 minus 4.4. That is 23.6. Okay, mega electron volts. That's the answer. It's option A. This is clear, everyone? Okay, good. All right, let's see next one. The binding energy per nucleon of lithium and helium nuclei are this thing and this thing respectively in nuclear reaction. So one lithium plus you have hydrogen gets converted to this thing. So this is a fission reaction. Okay, this is a fission reaction, right? So tell me, so we have this formula. The value of Q released is, okay, or let me copy paste this thing, this whole thing. So EBR is suppose binding energy of reactants. Sorry, BER is binding energy of reactants. BEP is binding energy of product. Then what would be Q? So Q is binding energy of product minus binding energy of reactants. Okay. So binding energy of product, how much is it? It is 2 times the binding energy of helium minus what is binding energy of reactants. So it is just binding energy of lithium, right? So here you might have a question. Okay, but let me wait. All right, so that is 2 times a binding energy of helium. So what is binding energy of helium? So there are 4 nucleons in each helium. Binding energy per nucleon is 7.06. So multiplied by, you have 7.06 minus binding energy of lithium is 7 times of 5.60. So this is 8 times this one. Okay, so 56.48 minus this would be 42 4 and then 39.2. So how much is it? 56.48. Okay, 56 minus 40 will give me 16.48. But I have subtracted 0.8 extra, so let me add 0.8. That will be 17.28. Okay, 17.28 mega electron volts, right? So it's option D. So this is clear, everyone? Is there a question? Nobody has a question? No questions. Good. Okay, so let me ask a question. Why didn't we take hydrogen 1,1? There are 2 products. We have taken both of them. 2 times the binding energy of helium. But we have taken only one reactant. Why not H11? So the reason for that is, what is there in H11 nucleus, hydrogen nucleus? There is only one proton. Okay, so binding energy is very less. Very less meaning, if you just give 13.6 electron volts to the hydrogen atom, the electron and proton will be separated. That's it. Okay, 13.6 electron volts and proton and electron are separated, and you can compare that with binding energies of these. So per nucleon it is some mega electron volts, right? Okay, so compared to that, the binding energy of hydrogen is very small. Okay, because it is hydrogen atom consists of one proton and one electron only. So if you remove electron there, what exists there? So what remains there is a proton only. Okay, so to make that proton free, how much of energy is required? Just 13.6 electron volts, and that you don't even have to give to nucleus, right? Because nucleus itself is a proton, free proton, you can say. Is this thing clear, everyone? Therefore the binding energy would be negligible. Clear, not clear? Okay, good. Yamini, is it clear? So what I'm saying is, in hydrogen you have, okay, what is binding energy? The energy required to free the nucleons, right? Energy required to free the nucleons from a nucleus. Okay, so you want to free the nucleons, means you want to separate protons and neutrons. Okay, that is the amount of energy. So whatever amount of energy is required for that process is known as binding energy. So now what's there in case of hydrogen nucleus? You have only one proton. Okay, so if you just remove the electron, and how much is energy of that electron in first orbit? It is just 13.6 minus 13.6 electron volts. So if you give 13.6 electron volts, only that much of energy, the electron and proton are separated. Okay, so we don't need to separately talk about nucleus also. Why? Because nucleus itself is a proton, right? And compared to that 13.6 electron volts, okay, compared to 13.6 electron volts, here the energy required is very high, right? We are not even talking here, we're not even talking about the energy required to remove the electrons. Okay, so here we talk about the energy required to separate the nucleus itself, that will separate the nucleons from the nucleus. That itself is very high, right? So that's why you can neglect the binding energy of hydrogen. It's very small. Okay, yeah, and that's it. That's the end of this chapter.